In the last lesson, we looked at encoding, storage, and retrieval. In this lesson, we'll look at this important process called system consolidation. It will be responsible for strengthening the cortical memory traces so that we have reliable and durable memories of information about our world stored in what psychologists would call semantic memory. We ended the last lesson with the brain state like this. We've got a strong hippocampal memory trace, but weak cortical memory traces. If we're going to have reliable long-term memory for the information we learned, we must strengthen these cortical memory traces. But how does the brain do it? Well, a clue can be seen if we reconsider what happens when we retrieve a memory. Recall that when we retrieve a memory, some cue has reactivated the hippocampal memory trace. Those hippocampal neurons then reactivate the cortical memory traces. But whenever neurons are activated together, synapses can go stronger between those activated neurons. In other words, reactivating a memory trace sets up the situation where the memory trace can be strengthened. And this is why retrieval practice is an effective study technique. Every time we retrieve a memory, we give the brain a chance to strengthen the neural connections between those allocated neurons, thus strengthening the memory traces. As it turns out, scientists have discovered that a very similar process happens during sleep. During sleep, allocated hippocampal neurons replay the day's learning. Hippocampal memory traces reactivate the cortical neurons that were allocated at the time of learning, and cortical neurons grow stronger synapses, making the memory traces stronger. So this was a really interesting discovery, that when we go unconscious at night and we sleep, there are various different stages of sleep, but scientists have gathered good evidence that what the brain is doing in certain stages of sleep is processing memory. The hippocampus now is being reactivated and sending signals to the cortex. The idea is that this communication, one of the purposes of this communication, is to strengthen cortical memory traces for the day's learning. Now, why would this memory processing happen during sleep? Well, cortical memories are stored in regions that were activated by the experience. So ongoing perceptual experiences would interfere with memory consolidation. Right? So remember, when we were sitting in class, we had, the experience of handling the microscope and seeing amoeba and paramecium, hearing the words and whatnot. Well, it was these areas of the brain, the sensory areas of the brain that were activated. Well, these are going to be the same areas that are going to store the memory traces for that event. But if we're going to strengthen these cortical memory traces, we don't want ongoing activity in these areas of the brain. We don't want to be seeing other things while we're trying to strengthen the memory traces of what we learned before. So during sleep, the cortex is not being activated by the senses. And this gives the brain a chance to selectively strengthen those cortical memory traces that were activated by the previous day's learning. So a lot of the system consolidation happens during sleep. It reorganizes the memory of the day's learning by making the cortical memory traces stronger. And one consequence of that is that the cortical memory traces then are less dependent on the hippocampus for retrieval. So notice I've made these now solid lines in the cortical memory traces. So we have a learning event, we go to sleep, and our brain is going to reprocess what we just learned. Hippocampal memory traces will be reactivated again while we're unconscious, the purpose of which is to strengthen the cortical memory traces, and this is best achieved if those areas of the brain are not being activated by, being awake and consciously seeing other things and hearing other things and feeling other things. So we want to do this processing when we're unconscious. A simplified way to understand what's happening during system consolidation: here on the left, we have our strong hippocampal memory trace. Notice I've pulled the hippocampus out of the brain here. We've got weak cortical memory traces, and system consolidation is simply going to strengthen those cortical memory traces. So there are dynamic events happening between the hippocampus and the cortex during sleep. The hippocampus is signaling the cortex to strengthen those cortical memory traces. Metaphorically, it's kind of like the hippocampus is teaching the cortex to make hippocampus independent memories. And those stronger memory traces includes those cortical areas originally activated by the experience. Again, so we're storing the memories in lots of the same places that were used to process the learning event in the first place. Now, repeated study sessions gives the brain multiple chances for system consolidation. Cortical memory traces can get stronger and stronger. So every time we study, right, we're setting up a situation where we are creating hippocampal memory traces that can be used then to strengthen the cortical memory traces during system consolidation. By repeating our study sessions, we can add growth, add new growth to old growth. Synapses can get stronger and stronger in these cortical memory traces so that we can really have reliable and durable memory traces of the information we're learning. The result of system consolidation is a network of strong cortical memory traces. Memory traces are linked in semantic memory so that partial activation of the network can reactivate the entire network. So we're kind of showing the concept of the amoeba here. Neurons here have been linked up to the visual memory trace of what an amoeba looks like, the memory trace of what the word amoeba sounds like, maybe the feel of the microscope. So what we've got here then is we're establishing the concept of an amoeba and paramecia. And we do so as a result of system consolidation. So system consolidation not only strengthens the separated memory traces in the touch cortex, visual cortex, auditory cortex, but also is linking together those memory traces to form the concepts of what we learned. Notice again the activation of the sound of the word amoeba can activate the concept of amoeba, and these neurons can activate the visual memory trace of what an amoeba looks like. So if I hear the word amoeba, I can imagine what amoeba looks like. If I see an amoeba, I can activate the concept and reactivate the memory trace of the word amoeba. This is sort of like another example of pattern completion. After sufficient system consolidation, the hippocampal index is no longer needed to reactivate the cortical memory traces. Frontal cortex retrieval systems can activate information stored in semantic memory. So now, if we've enjoyed system consolidation and we've strengthened those cortical memory traces, now we can access those memory traces with other brain systems. Frontal cortex memory systems can reactivate this information stored in the cortex, and we don't need the hippocampal index anymore. And this explains why older semantic memories are preserved in patients like HM and Clive. Successful system consolidation created strong cortical memory traces. So for all those cortical memory traces that are strong as a result of system consolidation, you can go ahead and remove the hippocampus or damage it by surgery or a virus or whatever and still have access to this information stored in semantic memory. So we'll wrap things up here by just asking a simple but deep question. What is a memory? Well, here we have sort of a kind of a diagram of a brain with a network of neurons, and maybe the white ones are being activated by the learning event. Here we have a close-up view of some bit of the brain, and again, the white ones are activated by the learning event. So what we've learned is that some subset of those neurons are going to be allocated to forming a memory trace, and the memory trace will be formed as they grow stronger connections with each other. Synapses get stronger, and that forms a network of neurons that then can be reactivated at a later time, and we can retrieve that memory. So we're going to say a memory is a pattern of strengthened synapses among allocated neurons activated by the learning episode. So take a moment to digest that. A memory is a pattern of strengthened synapses among allocated neurons activated by the learning episode. To review then, we'll recap this. Remember our 3 stages here. We've got the allocation stage. Allocated neurons will be the ones changed by the learning event and used to store the memory. Growth of stronger connections between allocated neurons is the formation of a memory trace That was neuroplasticity. We had plasticity in the hippocampus and the cortex, but there was greater plasticity in the hippocampus than the cortex. And that was the point of system consolidation, that we needed to strengthen those cortical memory traces. Because of plasticity, allocated neurons form a network that can be reactivated, thus recreating a pattern of neuron activity similar to what occurred during the original learning event. So retrieval is when we're reactivating that network of neurons that was formed during the storage stage. And if we successfully reactivate that network, we will successfully retrieve a memory. So let's get back to the school situation. In a school setting, we want to effectively transform episodic learning into long-lasting semantic memories. Being educated means having lots of information in semantic memory, but of course it got there from episodic memories. So here we see the now simplified version here. Every time we have a learning episode, we are sort of enjoying a moment that can be stored as an episodic memory, but often we forget the circumstances of learning. However, if we have successfully done system consolidation, we will be storing lots of information in our semantic memory. So we want to, as we approach school, and if we want to be effective learners, we want to understand a little bit about the human brain. And then now we're starting to see why it is that certain study techniques are better than others. So to recap then, when we're in school, we need to pay attention, because attention is one of those factors that enhances the strength of those hippocampal memory traces. If we're not attending to what it is that's happening around us, we're not going to be forming strong hippocampal memory traces. We need to make strong initial hippocampal memory traces so that that can be used to teach the cortex later on. We must be paying attention to what we're learning. In addition, practicing retrieval is a great strategy. Every time we reactivate the cortical memory traces, we can make them stronger. Of course, we need to get our sleep. A lot of memory consolidation is happening during sleep. And we want to repeat our study sessions. And very importantly, spaced out in time. When we repeat study sessions, we set up new hippocampal memory traces that can be used to strengthen the cortical memory traces. But we need to space out our study sessions in time, because the synaptic growth, the growth between neurons, takes time. We don't want to be spending long hours studying the same stuff. You want to space out your study sessions. Give your brain a chance to do the growth that is the process that strengthens these cortical memory traces. This then completes our series on the anatomy of memory.